Hey guys, welcome back to our biochemistry series of We.The.Doctors. I am Omkar and today we are going to continue our previous video about classification of carbohydrates. So if you haven't watched that video, I have provided the link in the I button, so please watch it. Let's begin with today's topic, that is polysaccharides, and let's start with homopolysaccharides. Now the term homo means same. So what is the same thing here? The monomeric units used in the polymer should be the same. That means if I'm using glucose in the chain of polysaccharides, so everywhere I should have glucose only. You can have some branches also, but all over I should have only glucose, only one type of monosaccharides only, then I can term it as a homopolysaccharide. Now if at all I have glucose, then galactose, fructose, let's say erythrose, and glucose, fructose. So here the type of monomers are different. We are using different types of monosaccharides, and if I try to hydrolyze them, I would be getting different monosaccharides. First I would be getting erythrose, then fructose, and glucose and galactose, right? But if I try to hydrolyze homopolysaccharide, I will be getting same type of monosaccharide. I will be getting only glucose here in this example. So such type of polysaccharide where I am having only and only one type of monosaccharide is called as homopolysaccharides. Now the linkages between these carbohydrates, these polysaccharides, which you can see, is nothing but O-glycosidic bonds. These are glycosidic linkages which are held together by an oxygen molecule. Now let's see it in deep. So if I have to draw a glucose molecule in Haworth projection, just draw an hexagon first and put oxygen here. And now listen carefully. This is C1, C2, 3, 4, 5 and 6th carbon will be tailing outwards because 6th carbon is not included in this ring. 6th carbon tails outwards, right? And at the first carbon, if the position of OH is downwards, then it's an alpha position. If at all I have drawn the OH at upwards, then it would be a beta position. Okay, so this is alpha glucose, and rest everywhere else the OH will be downwards only, except at the third position. We all know that at third position the position of OH changes, and at the 6th position also there will be OH. Only the 5th carbon, the OH will be absent because it is already holding the 6th carbon here. So remember, at the 5th carbon we won't have any OH, and at the first carbon if the OH position is downwards, then it would be alpha glucose, and if present on the upwards, then beta glucose. Let's draw one more glucose. So first hexagon and then put the O here, and everywhere else the OH will be downwards except at the third position. 5th carbon doesn't has any OH, rather it has a tailing of 6th carbon which is also having an OH. So glycosidic bonds are formed anywhere, can be formed anywhere where we have OH. So here let's number them. This is C1, 2, 3, 4, 5 and 6. Here also 1, 2, 3, 4, 5 and 6. Here we can form a glycosidic bond between first carbon of first glucose molecule and fourth carbon of second glucose molecule. This is also alpha glucose, and here as you can see we have two OH placed adjacently, and if at all I remove water from it, I will be getting a glycosidic bond. So it would be looking somewhat like this. So now it would appear just like this. So this is our O-glycosidic linkage, where the bond is mediated by, it is held upon by one oxygen atom. That's why O-glycosidic linkage. Simply you can call it as a glycosidic linkage. Now what do we get when we link two glucose molecules? We get a maltose. But if at all I have to form a polysaccharide, then I can expand this. I have to keep on adding the glucose with glycosidic linkages, and here also, similarly here also, right? So here entirely we are having a polysaccharide of glucose, alpha glucose. But this type of linkage will be alpha 1,4 glycosidic linkage. Why this alpha? Because the C1 carbon and the C4 carbon are having OH at downwards. The stereochemistry of both the carbons are same. But what if the stereochemistry changes? At that time, let us see example of lactose sugar. Lactose is a disaccharide of galactose and glucose, right? So we have to draw beta D galactose, hexagon, and then oxygen. See, the beta D galactose looks similar to glucose only. The only difference is that everything will be the same, but the C1 and C4 we have to swap. So here OH will be upwards, and here also OH will be upwards. In glucose it was downwards. In galactose, in beta D galactose, we have to put this upwards. The rest all remains the same. Here OH downwards, here OH upwards, and here tailing of OH, right? This is our beta D glucose, beta D galactose. Why this D? Because it has formed from the D galactose. In the Fischer projection it was D galactose. Here also this is alpha D glucose because it was formed by D glucose, right? And then alpha glucose. Now here the C1 carbon of beta D galactose has OH upwards, and C4 of alpha glucose is having OH downwards. So here the stereochemistry is changing, and at that time the bond formed is beta D galactose, and it would appear somewhat like this. What is this? Beta D galactose. This is beta 1,4 glycosidic linkage, and we are joining beta D galactose with alpha glucose. What are we forming? We are forming lactose. So this was alpha 1,4 glycosidic linkage, beta 1,4 glycosidic linkage. We have discussed both the types of glycosidic linkages, and this 1 and 4 is because we have formed the glycosidic bonds between 1 and 4th position. But as I said, the OH, wherever the OH is present, we can form a glycosidic bond. So it is not a compulsion. We have drawn here 1,4 linkages, but the linkages can also between C1 and C3, C1 and C5, not 5. 5 is not having any OH. So C1 and C2 also, right? So that depends on which type of homopolysaccharide we are talking about. We will be seeing different types of glycosidic linkages. Between 1 and 4 is common if we have to draw a linear chain, and branching is commonly seen between first and sixth carbon. But in some homopolysaccharides, the branching has also been noticed between 1 and 4, 1 and 3, 1 and 2 also. Let's continue with a famous example of homopolysaccharides, that is starch. So starch is basically a storage polysaccharide where the plant are storing their energy giving compound, that is glucose, in the form of starch. So it is a storage carbohydrate, and it is mostly seen in every plant, but there are some plants in which they are present in high concentrations, like vegetables, roots and tubers, cereals, etc. So mostly starch can be found in high concentrations in these, but basically it is present in every plant because it is a storage carbohydrate and plants require them as their energy. Now this starch also has two types, that is amylose and amylopectin. So the difference between them is that amylose is water soluble, whereas amylopectin is water insoluble. Amylose, it exists as 15 to 20% on Earth, whereas amylopectin exists as 85 to 80% on Earth. And most importantly, amylose is a linear chain starch, whereas amylopectin is branched in between. So tell me, if at all the amylose is only linear, which kind of glycosidic bond can be possible here? Only alpha 1,4 linkages can be possible, right? And here in amylopectin we can have alpha 1,4 as well as alpha 1,6. The branching is usually present at alpha 1,6. So it looks somewhat like this. So in amylose we know there will be only linear chain of starch, so there will be only bonds between 1 and 4 carbon, C1 and C4, C1 and C4. But in amylopectin branching is also present. So the branching is at 1,6 position. That means this is C1, this is C6. So the branching should be present between these two carbons. And if at all we remove the water molecule from here, we will be getting a bond somewhat like this. This is alpha 1,6 glycosidic linkage. Such type of branchings are present in amylopectin, and in amylose it is simple linear 1,4 glycosidic linkages. Now, since our lower classes we are studying this, that in our body there are some amylase enzymes present which are breaking down our carbohydrates into monosaccharides. So basically the polysaccharides are being broken down into monosaccharides. But how is that exactly happening? Let us apply some biochemistry in our use. So what happens is enzyme amylase is hydrolyzing these linkages, and the amylase which we have is alpha amylase, which can hydrolyze the alpha glycosidic bonds and not beta glycosidic bonds. That's why cellulose, being having beta glycosidic linkages, cannot be hydrolyzed by humans. That's why we cannot digest cellulose, because we don't have such enzyme for digesting the beta glycosidic linkages. We have alpha amylase which can hydrolyze alpha bonds, but the amylase is present in our mouth as salivary amylase and in intestines as pancreatic amylase. So by the first action of amylase itself, the carbohydrates, the polysaccharides are not broken down entirely, they are broken down partially, gradually. So the partial hydrolysis of polysaccharides produces what we call dextrins. So our next topic of discussion would be dextrins. So what are dextrins? They are the partially hydrolyzed forms of polysaccharides by action of enzyme amylase, right? So for example, we are having a big branched chain of carbohydrate, a big polysaccharide, and we are breaking it down by the action of amylase. So let me draw amylase. We are hydrolyzing it by the action of amylase, and what we get initially would be dextrins. So by the first action, suppose I got this chunk of dextrin. This dextrins will be called as amylodextrins. Further, if the amylase acts on them as well, we get erythroamylase. So what are erythroamylase? They are the more smaller groups of dextrins which on the action of iodine gives red color, and then at last we get achromodextrin. We get acrodextrin. So this is our erythrodextrin, and this is our acrodextrin. Erythro means on the action of iodine we are getting a red color, and acrodextrin means the iodine action has no color. So by adding iodine also I'm getting no color. That's acrodextrin. And after dextrins we will be getting oligosaccharides, then disaccharides, and then finally monosaccharides, which are our simple absorbable forms. So what are dextrins again? They are the partially hydrolyzed forms of polysaccharides, and when we use the enzyme amylase, we can get different kinds of dextrins. Firstly we can get amylodextrins. Then when we further hydrolyze it by the same enzyme amylase, we will be getting more smaller groups of dextrins, which is called as erythrodextrins, and then further more smaller groups called as acrodextrin. Our next important homopolysaccharide is dextrans. Now the dextrans are also homopolymer of T-glucose only, but the difference between the other homopolymer of D-glucose like cellulose, glycogen, starch is that these are found in humans, but the dextrans are found in bacteria and yeast. Plus, one more difference is that here the main chain is of alpha 1,4 glycosidic bonds, and the branching is of alpha 1,6 glycosidic bonds. In cellulose we have beta, but the number is same, alpha or beta, because cellulose is having beta bonds, but the number remains the same, the 1,4 and 1,6. But in the bacteria and yeast, the dextrans are having alpha 1,6 glycosidic bonds as its main chain, and alpha 1,3 glycosidic bonds as branching point. So this is branching, and this is main chain. And sometimes we might also see 1,4 and 1,2 bonds as well as branching. So if we look the structure carefully, so here we have glucose, because alpha 1,6 is the main bond here. So this is our another glucose. So do it here. 2. So 2. Right, and the bond is between this 6th carbon and 1st carbon, like this. This is our alpha 1,6 linkages. These are present as the main chain, and it continues further. And the branching points, as we discussed earlier, has alpha 1,3 bonds. So 1, 2, 3. Here we will be having branch alpha 1,3 bond, and then rest is the same, right? But at some points this branching can be present at the C2 carbon as well, and at that time we call it as alpha 1 2 bonds, somewhat like this. This is C1 C2 and this is C1, so alpha 1 2 bonds, and at some points it may present in fourth position as well. And when it's present in the fourth position, 1 2 3 4, this one, and this will be alpha 1 4, this is alpha 1 2, and here it is alpha 1 3, alpha 1 6, alpha 1 6, alpha 1 4, alpha 1 3 and 2. Okay, but if the dextrins are present in the bacteria and yeast, why are we learning it? Because dextrins have some biomedical importance. And what are they? The first importance is formation of dental plaques. So imagine we have a teeth here, embedded comes, and we have some bacterial colonization over it, or normal bacterial flora of the teeth. Now, these bacteria are leuconostoc mesenteroids, and these are non-pathogenic species. They are non-pathogenic. They don't produce some disease as such, but what happens is that they produce some enzymes. They produce enzymes which convert sucrose into some sticky substances called as dextrans. So here all around we will be having dextrans, and this forms a plaque. Now if these plaques are not removed when they are soft, they can get hardened, and gradually it may decay your teeth as well. So it is better to get rid of these plaques. Second biomedical importance is its use as plasma expander. See, whenever there is a patient who is having a severe blood loss, maybe it is an accident case, and the patient has lost around 1 to 1.5 ml of water, 1 to 1.5 ml of blood. So at that case of severe blood loss, there will be decline in blood volume. Eventually BP will fall down, and there can be strokes, there might be heart failure, liver failure, kidney failure. In short, multiple organ failure, right? So our best management as a doctor is first blood transfusion. But as we all know that the blood transfusion can be done only in some limited volume, like 500 ml to 600 ml, not more than that. So at that time, our second best option is to use dextrans. Now why only dextrans? Why not any other compound? Because dextrans, being a carbohydrate, is non-toxic, first point. Secondly, you might ask me that there are other carbohydrates also, for example mannitol, which is also a plasma expander, but mannitol is not preferred over dextrans because mannitol can be excreted by the kidney very easily and very quickly, but dextrans stay in the circulation for a long time, and 100 ml of dextrans can raise the blood volume up to 860 ml. So even infusing the patient with 100 ml of dextrans can raise the blood volume by 860 ml, and we can restore his blood pressure. Now, there is one disadvantage of using dextrin, which is if we take blood sample after using dextrans hampers with blood grouping. So, if we are taking the blood sample of the patient after infusing with dextrin, we might get false blood group. This is because in presence of dextrins, there is Rolex formation. That is Rolex formation. So what happens here is the RBCs get stacked upon each other, due to which the agglutinins are not so exposed. This stack formation is called as Rolex formation, and dextrins accelerates such kind of formations because dextrins are sticky. So to avoid that, the blood sampling should be done before infusing with dextrins. Now, inulin is our fourth kind of homopolysaccharide, and it is also a storage polysaccharide just like starch. But the difference is here the monomer is beta D fructose, unlike the starch in where we have glucose as our monomeric unit. And the glycosidic linkages are also different. Here we have 1-2 glycosidic bonds. So if we draw the structure of inulin, we will be drawing fructose here. Fructose is a 5-ring structure but 6 carbons. How it is possible? Because the chains, the tailing chain will be at 2 positions. The C1 will also be tailing, and C2 will and C6 will also be tailing here. So if the tailing of the C1 is present upwards, then it is beta, and the tailing if present at downwards, then it is alpha. So it depends where the C1 is present, and here we want beta D-glucofructose, so we are tailing the carbon downwards. And this is C1, this is C2, and the bond is between C1 and C2. So if I draw next fructose here, the bond will be present here. Again, this is C1, this is C2, and the story repeats. Again, there is a glycosidic linkage. This is 1, this is 2. So this is our inulin structure, and inulin is also having some biomedical importance in our diagnostic tests for estimation of GFR and body water volume. Inulin is mostly seen in tuber plants. Now the next kind of homopolysaccharides is glycogen, and it is the storage polysaccharides in humans, in higher animals, in all higher animals like us, right? So basically there will be glucose which will be linked by alpha 1,4 linkages, and the branching will be at alpha 1,6 position. But amylopectin was also similar. Then what is the difference? The difference between amylopectin and glycogen is that amylopectin is lightly branched, but glycogen is profusely branched, and it is branched as such that it looks like a tree. So glycogen has tree-like profuse branching. Rest things about glycogen we will be learning in glycogen metabolism further. Let's jump to our next polysaccharide. Now cellulose is the most abundant polysaccharide on earth. Most abundant. And it is a linear chain polymer. Linear means unbranched. It is a structural polysaccharide. Up till now we were learning about storage polysaccharides. Cellulose is a structural polysaccharide in plants, as it forms cell wall of plants, right? And here the monomer is beta D glucose, which forms beta 1,4 glycosidic bonds. There won't be any other glycosidic bonds because it is a linear chain polymer, right? So we will be having glucose, and beta means at C1 the OH will be present upwards, right? Rest all will be the same. Here we have next glucose, same hexagon oxygen. At C4 the OH is present downwards, right? But the stereochemistry of C1 and C4 is not different, due to which what will be formed? Beta bond, right? So this H and OH will get out and we will be having a beta bond, right? And similarly, lots of beta bonds, and the chain continues, right? This is the structure of cellulose. This is C1, C4. So it is beta 1,4 glycosidic bond, right? Now, as our body does not have beta amylase, it has only alpha amylase. We cannot digest cellulose as such, but cellulose is a very important dietary fiber. It is an important dietary fiber. Now what does this fiber do? If it is not getting digested, then what is its role? If it is not getting digested, then what is its role? Dietary fibers makes the digestion process slower. So if the digestion is slow, or food is getting passed on through the entire GI tract slowly, right? It is moving through our intestines slowly, and if the food is present already in our GI tract, will we be hungry again and again? No, right? So there won't be much appetite. Plus, the amount of glucose getting absorbed by the intestines will be optimum, and with time a constant amount of glucose will be received by our blood, eliminating the problems of hyperglycemia and hypoglycemia. So that's why dietary fibers are suggested to the patients who are having diabetes problems or hypoglycemic patients, because the glucose is getting absorbed constantly for hours, and that's why there is a balance between the transfer of glucose from GI tract to the blood and from blood to the tissues, right? But in cows, the cellulose can be digested. That's why cows can have plants like grass which are rich in cellulose, and by having such enzymes which can digest cellulose also, cows have 4 stomachs. Cows need 4 stomachs for digesting, for hydrolyzing the cellulose. That tough cellulose is. So if we talk about hydrolysis of cellulose, cellulose on hydrolysis provides cellobiose. It is just an intermediate substance, just like dextrins, as we saw. When we broke down polysaccharides, we got different kinds of dextrins, amylodextrin and erythrodextrin and acrodextrin. Similarly, after partial digestion of cellulose, we get cellobiose. And then after complete hydrolysis, finally the monosaccharides, which are beta D glucose. Alright. Our today's last homopolysaccharide will be chitins. So chitins are also structural polysaccharides, and they're mostly seen in animal kingdom, protecting by forming an exoskeleton in insects, crustaceans, right? And in some fungi also we can see chitin as the cell wall. They are the second most abundant polysaccharide on earth. And the monomers here will be NAG, NAG, of which we had heard in our NEET times also, right? In the preclinical entrances we have heard about a NAG, which is N-acetyl D-glucosamine. So these will be our monomeric units, and the bond will be beta 1,4, just like as we saw in cellulose. So first let's draw the monomer. Simply we have to draw glucose only. The root word is glucosamine. So OH, as it is beta, so OH will be upwards, downwards, upwards, downwards, and retailing. And here we will be having an amine group instead of OH. Let's draw an H here, H2, because it is glucosamine, and the side chain contains acetyl group at the attached to the nitrogen, so that's why N-acetyl. And attached to the nitrogen will be acetyl. Here the nitrogen valency should be 3, so 1, 2, 3. This is acetyl chain, this is glucosamine, and attached to the nitrogen should be the acetyl, so N-acetyl D-glucosamine. And here also same structure. Now look here. Here the bond will be beta 1,4. So we know how to draw it, right? It is very much similar to cellulose only, but the difference here is presence of this N-acetyl chain, right? And the cellulose was forming the structural polysaccharide. It is giving protection to the plants as forming their cell wall, whereas the structural polysaccharides here in the chitin is protecting the insects, crustaceans and fungi by forming their exoskeletons and cell wall in case of fungi. So these were our homopolysaccharides. In the next video we will be covering about heteropolysaccharide. If you enjoyed the video, please click on the like button, subscribe to our channel We.The.Doctors, and share this video to your friends. Thank you.